This Nyquist plot was obtained for a conditionally stable open-loop system. We want to evaluate the stability of the closed-loop system. To do that, we need to know the number of unstable poles in the open-loop transfer function and the number of encirclements of -1. This example doesn't give the transfer function, but the statement of the problem has a very important piece of information. The system is said to be conditionally stable when in open loop. A conditionally stable system has poles that are located along the imaginary axis. This is what we also call a marginally stable system. Given that the poles are located on the imaginary axis and not to the right of it, then you can say that the number of unstable poles of the open loop transfer function is 0. The real part is 0, it's not positive. So P for this particular system is 0 for a conditionally stable system. This is the location of the poles for the open loop system. The question now is the closed loop system stable or unstable? To do that, we need to look at the Nyquist plot and count the number of encirclements of -1. -1 is here. To count the number of encirclements, we can simply trace a line from -1 towards infinity anywhere on the Nyquist plot, and now count the number of times the Nyquist plot intersects this line and in which direction. We see that here it will cross that line once, and that will be in the counterclockwise direction. Here we are crossing the line again in the same direction, in the clockwise direction. So for this particular point here, we see that the number of encirclements is +2. Is now the system closed loop stable or unstable? Well, the number of unstable poles of the closed loop system is simply P plus N, and this is equal to 0 plus 2, 2. So the system is closed loop unstable. These two poles will now migrate to the right side of the S-plane, and you'll make the system closed loop unstable with two unstable roots. That's what we see here. The second question is, let's assume that we multiply this Nyquist plot by a certain gain. The Nyquist plot will now expand to the left, and -1 eventually moves inside this loop. If -1 is now here, will the system be stable or unstable? If this is where -1 is, and again, we can do that by multiplying the entire Nyquist plot by a gain, it will just expand to the left. We can use the same analysis, have a line tending to infinity, and now count the number of encirclements of -1, or how many times the Nyquist plot crosses that line. Here we have one crossing, and this is in the clockwise direction, so this is +1. And here we have another crossing. This is now in the counterclockwise direction, so here is -1. So the net number of encirclements of -1 in this specific scenario is 0. So for this one, we have N equals to 0. Now, would the closed loop system be stable or unstable? Well, let's use the same formula. Number of unstable poles equals to the number of unstable poles of the open loop transfer function plus the number of encirclements of -1. And this is now 0 plus 0, which is 0. The closed loop system in this particular case is closed loop stable.